In this tutorial, we will talk about binary numbers. I will start off by writing an example number, 2538. In elementary school, you were taught that the rightmost digit is the ones place. Moving left, we have the tens place, the hundreds place, and the thousands place. Another way of looking at this is using the number 10 as a base. The base 10 number system is more commonly known as the decimal system. We use exponents on the number 10 to write the place values. 10 raised to the 0 power, 10 raised to the first power, 10 raised to the second power, and 10 raised to the third power. We can see that 10 raised to the 0 is equal to 1, 10 raised to the 1 is equal to 10, 10 squared is equal to 100, and 10 cubed is equal to 1,000. In a base 10 number system, every number from 0 to 9 is available to use. In our example, we see the first number 2 and we know that it represents how many thousands there are. Likewise, we see that there are 5 hundreds, 3 tens, and 8 ones. The numbers 2, 5, 3, and 8 are called weights. We decode numbers by taking the weights and multiplying them with their corresponding place value. Then we add up all of those products. For example, 2 times 1,000 plus 5 times 100 plus 3 times 10 plus 8 times 1. Of course, once we add all of those products back together, we get our original number, 2538. Sometimes it's more convenient to use a number other than 10 as the base for our system. Devices that use digital logic, such as computers, are designed using the base 2 number system, also known as the binary system. Like base 10, any number less than the base is available to use. For binary, this means 0 and 1. To build our binary reference table, we take the number 2 as our base and use increasing exponents like before. We start with 2 raised to the power of 0, 2 raised to the power of 1, 2 raised to the power of 2, and 2 raised to the power of 3. If we calculate that out, we have 2 raised to the 0 is 1, 2 raised to the 1 is 2, 2 raised to the 2 is 4, and 2 raised to the 3 is 8. Here's an example base 2 number, 1011. How do we make this binary number meaningful to us? We do what we did in our base 10 example. First, we take the weight of each place and multiply it by its corresponding place value. Then we sum up those products. In this case, we have 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1. Simplifying this gives us 8 plus 2 plus 1, which equals 11. An important thing to note is that when dealing with different bases, it is often convenient to write a number with the base you used in parentheses. Here is how we would write our 2 example numbers, 2538 base 10 and 1011 base 2. Let's practice reading numbers in base 2 by converting them to base 10. Here's an example number, 0111 base 2. We want to know what this binary number is in the decimal system. The conversion process is simple. Remember, we multiply the weights with their corresponding place value, then we sum up all of those products. In this example, we have 0 times 8 plus 1 times 4 plus 1 times 2 plus 1 times 1. When we simplify this, we get 4 plus 2 plus 1, which equals 7. I want you to try one on your own. Take the number 1101 base 2 and convert it into base 10. Pause the video and come back to check your answer. To convert 1101 base 2 into base 10, you take 1 times 8 plus 1 times 4 plus 0 times 2 plus 1 times 1. When we simplify this, we get 8 plus 4 plus 1, which equals 13 in base 10. Let's try something that's a bit trickier. Let's take some base 10 number, such as 6, and convert it into binary. How do we go about doing that? Pause the video and see if you can figure it out. The way we approach this is we take a look at our reference table and see which binary digits we are going to have to use. Since 6 is greater than 1, we know that we have to use the first digit. Since 6 is greater than 2, we know we have to use the next digit. 6 is also greater than 4, so we know we have to use that digit as well. However, 6 is not greater than 8, so we know we don't have to use any more digits to represent 6 in binary. Remember, we need these digits to add up to our target number 6. We will start with the largest digit we selected 4, and we will add to it the next digit 2. 4 plus 2 gives us 6, just what we wanted. What do we do with the leftover 1? Since we don't need it, we just add 0. Now we need to fill in our binary weights in the appropriate places. We didn't use the 8's place, so we put a 0 there. We did use the 4's place, so we put a 1 there. We also used the 2's place, so we put a 1 there. We didn't use the 1's place, so a 0 goes there. Now we have our result. Decimal 6 is equal to 0110 in binary. To finish off this tutorial, we are going to take the decimal number 15 and convert it to binary. The process is the same. We need to figure out which binary digits we will need to construct the number 15. Since 15 is greater than 1, we know we'll need the 1's place. 15 is greater than 2, 4, and 8, so we'll need those places as well. How do we know if we need any more digits? Remember that this reference table continues on. The next place would be 2 raised to the power of 4, which is equal to 16. Since our target number 15 is not greater than 16, we won't need that place. We start with the largest digit we selected, and add 4, which gets us to 12. We add the next digit 2 to get us to 14. Finally, we add the last digit 1 to get us to a sum of 15. We will fill in the binary weights by asking ourselves if we used that place. We used the 8's place, so we fill in a 1. We used the 4 place, so it gets a 1. We used the 2's place, so it gets a 1. And we used the 1's place, so it gets a 1. The decimal number 15 is 1111 in binary.